بسم الله الرحمن الرحيم والصلاة والسلام على نبينا محمد وعلى آله وصحبه أجمعين. Okay, so this is lecture 2 of chapter 5 on linear regression. And today we are going to talk about assessing the model performance of a simple linear regression that we've started in the last lecture. And also we'll talk about the multi-feature linear regression, where we have more than one predictor. So let me make a summary. In the previous lecture, we have introduced the simple linear regression model, which actually captures the relationship between two variables, one that we call the independent variable x, which is the feature, and also the dependent variable, which is y, called the output as well. So in our case, we had as input variable or independent variable the television budget, and the output was the sales, okay, based on the budget made on advertising. And the equation in the simple linear regression is captured by the equation of y equal to beta 0, which is the intercept, and beta 1, which is called the slope. And you will have a certain noise factor, which is the error term that captures the variation between the real data, okay, and also the model. We have also introduced how to calculate, using a mathematical closed form, the slope beta 1 from the input and the output from the data set. And same thing also, we can find the value of the intercept beta 0, okay, using the average of the y value minus beta 1, which we find here, and the average of x values. And we made also the coefficient evaluation using the hypothesis testing by assessing the statistical significance of the p-value and the t statistics based on some threshold. So that was the summary of the previous lecture introducing the simple linear regression model. But now the question of today is that, having a model, how do we assess, how do we evaluate the accuracy of the model? How well does the model fit the data that we have in the data set? So the objective of model accuracy is to assess how effectively the linear regression model predicts the output. In our case, it's the same, based on the input, in our case is the TV advertising budget, and also provide insights and interpret the results to optimize the marketing strategy. So when we do actually a prediction model, is not just to have a fancy model, but to help us, for example, optimizing the processes, and in our case, increasing the sales and the revenues. So there are two standard ways on how to measure the model accuracy. The first one is called the residual standard error, RSE, and is calculated using the equation, the square root of the sum of yi minus y hat. What is yi minus y hat? Is basically this distance between the predicted value and the actual value. Okay, so we're going to make the average of all the green lights. Okay, this will give us the average standard error, or what we call the residual. Residual is basically the error, we call them residual. And you calculate the average, and here it's n minus 2 and not n. So, yes?
This converge to a normal distribution where we can say it's a central limit here?
No, here usually we assume that the estimated error is normally distributed. Okay.
In the beginning.
Yeah. And here it's divided by n minus 2. So 2 here represent the number of coefficients to predict. Okay, so here we have two coefficients, beta 0 and beta 1. Yes, so if we have more weights, as we are going to see, so we need to make minus k, the number of weights, minus 1. Okay, so this measures the average magnitude of the residuals, or of the error, between the observed values and the predicted values. The second way on how to assess the model accuracy is to use the coefficient of determination, and is denoted as r squared, and it has the following expression: 1 minus the sum of the difference between prediction and actual values, and here is the sum of difference between observed values and the mean. We will explain this in each slide. And basically this r squared is interpreted as the percentage of explainable variance, or the percentage of the response variable variation that explains the linear model. So we will explain this just in a while. Let's start by the first metric, which is the residual standard error. And it measures the average distance between the observed values and also the predicted values, and is mathematically expressed as the square root of the RSS. RSS is the sum of the residuals. Okay, residuals, it means the difference between the predicted and the actual values, divided by n minus 2, and 2 is the number of estimated parameters. And the RSE quantifies the typical error in prediction. So for example, if you have a linear model, you know in average you're going to have some kind of discrepancy, the average discrepancy between your prediction and the actual value. Now let's, for example, apply this in our context of sales. So this plot represents in blue the actual values and in red the predicted values, and we calculate the average. Okay, so the average of all these residuals. So applying this formula, here we have 200 observations, and we can calculate the RSS from the data set. We will find 3.26. So since we are using $1,000 as a unit, so we'll multiply this, we'll find that the average deviation in sales is around 3,260 units, which is, I think, in thousands of dollars. Okay, so if, for example, you make a prediction here, in average, you will be $3,000 plus minus in the sales. Okay, for example, you spend a certain TV budget, and you find an estimation based on this regression line. So the estimated error will be around $3,000 in the sales. It could be plus or minus that average. So whether this value is high or low, we need to make it as a percentage. So now, if we average all the sales, we will find that the average sales across all the markets is $14,000, and the average will be here 23%. So the error in the prediction is 23%. Now, whether this is considered as high or small, it depends on the context. So usually, in context like this, it's considered as acceptable, but in other contexts, like for example in physics or something that is more critical, it could be considered as not sufficient. Okay, and the model maybe is not sufficient to express, okay, the data set. Yes. Okay.
Why did you multiply the RSC with the total?
Sorry?
Why did you multiply to get the average deviation?
Yeah, this one is just to make it standardized with respect to the average sales. Okay, now, this is the margin of error. Is it high or low? You don't know. Now, if we divide with the average, that will give us a percentage.
So what is 1,000?
Huh? Yeah, if you look at the data set, if you have 2.3, it means 2,300. So we multiply by $1,000. Yeah, because all the value were divided by 1,000, not to have big numbers. Okay, so here we have a deviation of 23% of the average sale. So that would be acceptable. I mean, plus minus, instead of 14,000 would be 15,000 or 17,000, 16,000, something not. Okay, it's not very small, but not very dramatic. I mean, we don't have 60%. Okay, of course, this model is simplistic. We can see like a high variation of the data. This model could be simplistic. Now, if we use more complex model like neural network, we could have something that would provide smaller error. Okay. So the significance here, so in sectors where accurate forecasts are essential, okay, 23% prediction error might be significant financial discrepancy. Okay, now it depends on your context. And comparing this LSE to previous model or industry standards, 23%, okay, we need to compare this value to the standard, whether it's acceptable or not acceptable. So now the second metric is the R-square statistic, which we use in linear regression, and it is called the coefficient of determination, which quantifies the percentage of the variance in the dependent variable, which is the output, that is predictable from the independent variable. Yani in simple words, if I make a linear regression between TV and sales, it's how much the TV budget affect the sales. It's kind of correlation. Okay, what is the level of impact of the television budget with respect to the sale? So the R2 square provide us like an indication about this type of relationship, and it is measured by 1 minus the residual sum of the squares, which is this one, the observed minus the predicted, and divided by the TSS, which is the observed minus the average. Okay, so in our case we find it's 61%, so we can say that the same depend on the television budget with the level of 62%. Okay, so this is how we can interpret it. And this is the full expression. Okay, so we're going to make 1 minus, this is the residuals, the sum of residuals divided by the sum of the observed value minus the average. Okay, and it can be written like this. So TSS can be here in the top. So basically TSS minus the RSS is denoted as the ESS, okay, which is the explained variance. Okay, and then we can divide by the TSS to get this percentage. Okay, so what does this term capture?
TSS.
Yes. So if this term is high, what does it mean?
High values.
Look, if this term is high, the R2 will be
High.
smaller. Yeah, I mean you have 1 minus. Okay? So the closer they are, the more relevance it will be. You have minus here. If you don't have minus, okay, so you have TSS minus the RSS. And, okay, so, okay, look at the TSS now. Yi minus the value. Now, this one, if it is high, okay, the impact is mostly here. If you have a lot of variability here, okay, so in this case, we will have less variance, okay, less explainability. If the observed is very far from the predicted, the explainability will be smaller. So it's basically this one, okay, if these two are far from each other, then we will have higher variance.
So is it R squared is the explainable values?
Sorry?
I thought R squared was the explainable values.
R square? Yeah, this is basically, this one is basically this one, same thing. It just TSS was, if I put TSS on the top, multiply here, TSS divided by TSS. What is 1? It's TSS divided by TSS. So you will have TSS minus RSS divided by TSS.
Oh,
Yeah, that's it. It's the same formula. Okay. Yeah. Okay. So the R2 square should not be also confused with the correlation coefficient, although they have some relationships. I mean, if we have high relationship between the input and the output, usually we have high also coefficient of determination. Now, applying this to the TV versus sales, if we calculate the R square coefficient, it's 0.62 almost. And the correlation coefficient, where we apply this formula, which is the correlation between the input feature and the output feature, we find 0.78. What does it mean, 0.78? There is a strong correlation between the input and the output. Here we don't use the predicted. Look, everything is from the data set. These are the features minus the mean. And these are the observed values minus the mean.
so the correlation coefficient is for the input versus the output.
The input versus the
R
output.
squared is for the predictions.
Yeah, for the predictions. And these should be somehow correlated if the prediction model is good enough. So in this case, we should have relationship.
Between them in
Yes.
their models, right?
Yeah. So if you have high correlation, in principle, a good model should give you high R square value coefficient of determination. Okay? If they are correlated, I mean, if the correlation between the TV and budget, so I expect that the coefficient of determination is also high. If it is not high, maybe your model is not good enough.
So R squared and the correlation coefficient are both denoted by R squared?
Yes, but you should not confuse them. Yeah. I mean, but okay, let's write it RXY square. Okay, or correlation. They are just notations. Okay, so this is a summary of all the metrics. Okay, this is the summary of how to calculate beta 1 and beta 0. Mathematically, also we have introduced the p-value. Okay, if the p-value is smaller than 0.0001, so in this case there is a relationship between the dependent and the independent variable. We use also the t-statistics to confirm the relationship between the dependent variable and the independent variable. Same thing also for F statistics. And we use, for assessing the model accuracy, not the coefficient accuracy, we use the residual standard error using this formula, and use the coefficient of determination using this formula. So this is just a summary of all the different formulas that we have introduced so far. Now, so far we have talked about only the regression between one predictor and one observed value, which is the same. But in some cases, like in our case, the model doesn't only depend on the TV. We are also spending budget on the radio and also on the newspaper. But the simple linear regression is not sufficient actually to capture all the predictor. We have only one predictor, which is X. So I can try X as a TV predictor, or as a radio predictor, or as a newspaper predictor. But this model is not sufficient to capture the interrelation between these different predictors. Maybe there is a relation between the budget spent on the radio and on the TV, or between the newspaper and the radio, and so on. So in order to have a better view about the impact of all these different predictors on the sale, it makes more sense to develop a regression model that captures all these different inputs. Okay, any question here?
Yeah, what's the difference between MSE and RSE?
So the MSE is just the average of the RSE. No, this RSE here, it's n minus 2.
Yeah.
Okay, so here 2 is the number of predictors.
Okay.
The MSE is just the average, so it's divided by n.
So it's almost the same.
It's not 100% the same, okay? By definition, they are different. Now, the value, whether they are close or not close, that's another story. Of course, if n is very high, they will be almost the same. But by definition, they are not. Of course, yes. You know, it will be in 2 predictors is nothing. Okay. They can be approximated, but they are not the same. Okay. So here it's clear that one predictor is not sufficient to capture also the influence of other predictors like X2 and X3. So in this case, we can have recourse at a multiple feature linear regression. And in this case, it will be the sum, a weighted sum of the coefficients, okay, with the predictors. Now I can put X1 as the TV budget, X2 as the radio budget, and X3 as the newspaper budget. And of course, we will have also random error, because the model is not going to capture 100% all the observed outputs. So this is how we represent a linear regression. It's basically with the 2-dimensional line. But in multi-feature linear regression, so here we can visualize in blue the actual sales, and in the red it's the predicted sales. So we can visually have an understanding whether they are close to each other or not close to each other. So from this figure we can understand that they are somehow correlated. The predicted are not very far. Okay, we don't have like clusters of red and clusters of blue. They are pretty much very close to each other. So we can, in this case, we can infer that the linear regression could be sufficient to capture this type of relationship. But now we need to talk about what will be these values: beta 0, beta 1, beta 2. We need to determine them. Of course, when you use multiple features, this will have an impact on the metric, on the RSE metric, because since the number of predictors is going to change, I have k predictors from 1 to k, and also have beta 0. So n we need here to divide by n minus k minus 1. In total, I have k plus 1 predictors. From beta 1 to beta k, these are k predictors, and plus beta 0, k plus 1 predictor. I start counting from 0. Okay, so this is now the general definition of the RSE for k predictors. Of course, if k equal to 2 or 3, n minus 2, yeah, k number of parameters, so it will be n minus 1, yeah. If I have 2 predictors, yes, in principle it's n minus k, yeah. Adjustment for k plus 1, yeah, we have k plus 1 predictors. So yeah, if I have 2 predictors, it will be 1 minus 1, so n minus 2, yeah, that's correct, yeah. That's the adjustment that we do for the RSE. So for the coefficient of determination, it doesn't change, but we have also the adjusted R2 square. And in this case, we account for the number of predictors to prevent overfitting. So the R2 adjusted is equal to 1 minus this sum divided by n minus k minus 1.
RSE over
Yes,
a multi-feature RSE over the linear regression RSE.
yes. Okay, so we have to make it adjusted here. That's the general coefficient of determination, and this one is the adjusted. So we're going to take here n minus k minus 1, which is this formula here, okay, the RSS. And the TSS will be divided by n minus 1. Of course, here when we have two predictors, it will be n minus 1 divided by n minus 1, and it will come to this formula. This is why in two predictors we have this formula. It's the same as the adjusted. But with k predictors, okay, we can make the adjustment as follows.
I just noticed, isn't the TSS just the variance? Because you're taking the mean and the difference between the mean square.
Which is the variance?
You can calculate.
Yeah, it's the variance, yes. It's basically the variance, yes, minus the average. Yes, this one.
Yes.
The TSS is the variance, yes. It's the variance. Okay, so we can also apply the same linear regression approaches to find the coefficients. Now look, solving this multi-feature linear regression, you can find this is the coefficient for the TV, okay, this is the coefficient for the radio, and this is the coefficient for the newspaper. What can we understand from this coefficient? What has the highest impact? The radio has the highest impact, and then followed by the TV, and then followed by the newspaper. And here we can calculate the mean square error, okay, which is 2.78, and the R squared is 0.9. What does it mean, 0.9? So this infers that you have a strong impact of advertising over the sales. Okay, so this advertising has strong effect on the increase of the sale. Yeah.
How can I read the graph on the top part?
Which one?
Top right.
Yeah, this is just a visual illustration about the distribution of the points, whether actual sales or predicted sales. So we don't see clustering. I mean, both they are very close to each other visually. But now, look, this is confirmed by the R squared, which is very high. Okay, it's 0.9. This means that there is a correlation. So the model captures very well, okay, the effect of advertising over the sales. This is how we interpret it.
So the predicted sales are far away from the actual sales? We cannot tell.
Yeah, we will have a smaller value of the R square metric. Is it clear?
It will have no big impact.
Yes. Okay. Okay, so now we can infer several interpretations from these coefficients. Okay, so analyze the impact of different advertising media of the sales. Now, since you have made a multi-feature linear regression, and observe here for the sales, the newspaper. If you remember these scatter plots. Okay, so of course this one, it's visually has the less impact. Now, in the beginning, we said that the TV seems to have better relation with the radio, but we discovered that it's not the case. Okay, and we can analyze this now for the slope of the TV budget. It's 0.045, and for the radio it's beta 2 0.18, and for beta 3 it's minus 0.001. So it's negative here, but it's very small value. It's almost close to zero, so it almost has no impact. Now, how can we analyze these coefficients? So here for the TV, it has a positive impact because you have the plus sign. It means if I spend on the TV, the sales will increase. A negative impact, if I spend on the budget, spend on budget, the sale will decrease, which is, okay, it's not, now, likely it's almost, but it's very negligible for the newspaper because it's very, very small. But if you have a very high negative coefficient, it means that will decrease the value of the sales, okay? So the magnitude is moderate, and the explanation that for each 1,000 increase in the television advertising budget, this is associated with an increase of 45 units of sales. In the radio, we have a strong positive correlation, okay? And for each 1,000 spent on radio advertisement, we will have 188 units. And here we have negligible to negative, but very weak magnitude. It almost doesn't have any effect, whether you put budget on the newspaper or you don't put badge on the newspaper, there is no major effect. This is why we use predictive models, is to have this kind of interpretation. Now, for example, in the project, this is what I care about, is what kind of insight are you able to extract from a predictive model, okay? And now if you are a decision maker, you will say, okay, probably I should invest more on radio, much less on newspaper, and moderately on
ستحتاج إلى فتح
on
قفل
television.
الآيفون
Okay.
أولاً.
Okay. So of course, this is the mathematical representation, and this is just a graph that shows, okay, on two-dimensional plane, this is the regression plane with respect to the different points from the data set here. Okay, so to finish this lecture, now you'd like to make implementation of linear regression on Python. We have already seen some code, but now I'm going to summarize you the different libraries, because there are different libraries that you must know about them and recognize them. They do some kind of complementary work on linear regression, and I'm going to explain you the differences of the Python library that are available to solve linear regression problems. So to summarize these libraries in Python, we basically have four main categories. So the first one is the OLS, which is the ordinary least square, which represent the foundational statistical method for estimating the least square of regression. So this method basically doesn't use machine learning. It uses closed form equation, mathematical equation using matrix manipulations. Okay, so it's basically numerical solutions without having to have a data set divided into training, testing. There is no training involved over here, because we can have a closed form equations from linear algebra that allows us to solve this problem. Okay, basically it's like you have a certain number of unknown variables, and you have known values that will help you to find these unknown variables.
I think we did this with the Hawaii.
Yes, yes.
They did matrix manipulation and derivative with the
Yes, it's an equation system. Basically, we're going to use an equation system with multiple unknowns to find out the solution. So there is no training over here. You have only one unique solution that we can, because linear regression is actually one of the simplest problems in machine learning. And also we can use machine learning by splitting into testing, training data sets, training on the test, and then making contrasting with accuracy on the testing data set. And we have also the rich and lasso regression, which are basically similar to linear regression machine learning models, but they use kind of regularization techniques in order to reduce the overfitting issue. And I'm going to explain this very briefly so that you know about that. So OLS uses the stats model library in Python, whereas all the other three variants, they use the scikit-learn. So scikit-learn is basically a machine learning library in Python that contains a lot of available functions, okay, like linear regression, support vector machine, decision trees. Several of the classification models, they are already built in and are available in the scikit-learn library. So let's explore all of them. We start by the ordinary least square for regression, and this is a simple script that also we apply here on the advertising data set. So the objective of the OLS is to minimize the sum of the squared residuals between the observed and the predicted values, and basically try to minimize the difference between the observed and predicted values over here. So in order to create a Python script, first of all, we need to import stats model .api as SM, so like here, and then you need to add a constant to the predictor, which is the beta 0, okay, which is the bias, we call it the bias, the beta 0, and then just sm.ols.fit, and you provide the y, which is our output, observed values, and the x, which is our input. And observe here, we're going to use the whole data set. There is no splitting. I'm going to load the whole data set, the features in x, the output in y, and then I use .fit. So .fit is going to do solving the system of equations, and finally provide a model, and model.summary will return all the information about that particular model, like the R square statistic, the adjusted R square, the F statistic, and so on. Okay, look here, there is a small difference between both because we have three predictors. And we will explore all these different values. So let's interpret these values over here. The R square, in this particular case, is equal to 0.89, which is almost 0.9, indicates that the proportion of the variance of the dependent variable, which is the same, can be predicted, okay, can be predicted by the independent variables. And the value suggests that this is a very good fit because it's very high, as 98% of the variance in the sale is explained by the model. It means the level of noise is only around 10% that cannot explain the sale. Okay, of course, if you have big discrepancy, in this case, the R square statistic will be very low. Okay, so the variance of the in the sales is explained by the model that we have, the linear regression model that we have derived. And the adjustment here, just we need to take into account the predictors to avoid overfitting, is slightly lower. So usually it would be slightly lower. Now we have also the intercept, which is 2.93. So how can we interpret the intercept? It means this is the predicted sale if there is no investment. If I don't put any investment, zero investment in newspaper, in radio, in television, so the sale is going to be around 2.93, of course, multiplied by 1,000 to find the number of units. And this is the proportion of the TV, which is the slope for the TV, the slope for the radio, and the slope for the newspaper. And we have already interpreted these different values. Okay, you will find them here, here, and here. Of course, you can find other statistics like the standard deviation, the t-statistics, the p-value, which allow to infer other information about that. We have the statistical significance and model fit with respect to the null hypothesis. So here we have the F statistics. Where do we find it? It's here. 570. It measures the overall significance of the regression. So a high value of the model means that there is a good fit between the input variables and the output variables. So the model captures very well the relationship between the predictors and also the sales. And this is also confirmed by the p-value, which is very small. Look, it's smaller than 0.0001. So all of this information, all of these results are consistent with each other. From the R square, from the F statistics, from the p-value, all of them are consistent.
So
Yes.
when the p-value is small, we can disregard the null hypothesis.
Yes, exactly. Is it clear for everyone? Okay. Okay, these are residual analysis that we will find here. Okay, test for the presence of autocorrelation in the residuals. So a value of 2.08 indicate a good independence among residuals. And residuals among the different predictors are independent. And this one, another test for normality. Okay, a high GB value along with a very low probability indicates that the residuals do not follow a normal distribution. These are just additional information about the residuals. So in this couple of slides, I provide the theoretical background, but I'm going to skip it. Just here if you want to have some more information about how OLS work from a mathematical perspective using matrices. And I provided also some numerical examples. Now the second technique is about the scikit-learn linear regression class. Okay, and here it actually applies the machine learning techniques. And the idea basically is to create a model using linear regression and then to split our data into a training and testing data set. So some part of the data will be used to train a model and the other part of the data will be used to test the model. Of course, so in contrast to the OLS, it will provide us a deterministic answer. Now, since we use machine learning, the answers are probabilistic. I mean, if you change the dataset split or the dataset that will be used in training, the result will be different. And it depends on how many times you're going to train your model. So splitting the dataset here, we're going to use X-train and Y-train to feed the model. And fit, it means we're going to train the model in order to find the linear regression coefficients. And then we can use model.predict in order to provide the prediction of with respect to the test features. So here we have Y predicted, okay, And we can determine the mean square error based on the test. Okay, so we will take y test minus y pred, and we calculate the sum of all, the average of the sum. This will provide us the mean square error. And we can extract the model coefficient and also the intercept using model.coef and model.intercept. And now looking at the output, we will find the coefficient. Look, it's very close to what we find in OLS, but it's not exactly the same. Okay, 1.89, it was 1.88, and this is slightly negative value. So the intercept is 2.933, similar to what we find in OLS. And the mean square error is 3.33, and the coefficient of termination is slightly lower than what we found with OLS. Of course, if you change the random state, if you change the test split size, all these values are going to slightly change.
What is the random state?
Huh?
Random state.
The
Random state.
random state, this is like the initial seed. If you put it the same, maybe it will produce the same thing. Okay?
Different samples.
Yes. So I provide you here, I have a notebook where you can try all these different functions. All the code is available in the notebook. I think I've shared it. If not, I'm gonna share it with you. And look now, this is now a comparison between linear regression with scikit-learn and the OLS. Of course, the OLS provide more information from the report, from the model.summary. And there are small differences, as we already mentioned. Okay, so the intercept here is slightly different from the intercept here. Of course, and we can play with the model size, okay, the test size, the training size, the random state to get different type of values, but they converge to, okay, close to each other. So these are the key differences, as already mentioned. Data splitting in scikit-learn, we do data splitting, while in OLS we use the entire data set. Okay, in linear regression, there are also regularization algorithms like the lasso and the rigid regression approaches. And the intercept handling, say both include an intercept with slight variation in normalization and calculations. So to improve linear regression, we can use cross-validation, we can use data normalization. I didn't use no data normalization here. I just use the raw data. And now this is the visualization of what the difference between the actual values and the predicted values. So usually they should all be around the line, okay, which is the line x equal to y, but you have slight variation. So this means that the prediction is pretty much close to the actual values. This is another 3D representation where we have the radio, the TV, and the newspaper, and we can see the increase of the sale, the predicted sale. So we can see from the color, the blue color is mostly correlated with higher radio values. Okay, so that are some of the ways on how we can visualize the output. Of course, if we have more features, it will be more difficult because I already used 4 dimensions here. X, Y, Z for the predictors and Y by the colors. It will be more difficult to accommodate visually more features. So the last one is about the ridge regression and the lasso regression. So basically we use the same thing. Instead of using linear regression, we are going to use ridge. And here we're going to use lasso. So what's the difference here is what to minimize. Okay, in ridge regression, so this is the mean square error that we usually minimize in linear regression, right? Okay, now we're going to add an additional factor, which we call the regularization factor. This one is called L1 regularization, and this is to avoid overfitting. Okay, so we try to change the loss function so it's not pretty much related to the training data. Okay, this factor is going to be always greater than the mean square error. So whatever I do is going to be greater than the mean square error, so I'm not going to train perfectly to the training data set. That's the idea of regularization in general. Okay, that's one of the factors. This is why it takes an alpha parameter, because this alpha will be the value that will be integrated into the loss function. Okay, other things are pretty much the same. So we use fit, predict, and we can define the coefficient, the intercept, the mean square error, and the R2 square error. It's just the name of the function that shows here. It's basically the same as linear regression here, but we're going to use this regularization factor. The lasso, the same thing. So here we're going to use alpha multiplied by beta square g. So we're going to add the squares of the coefficients, and here we're going to use the sum of the absolute value, and this is called. So yeah, this two is L2 regularization, and this one is L1 regularization. L2 because of the square.
So the beta j.
Yes.
This is the sum of all parameters.
All coefficients, yes. All coefficients or parameters. Yeah, it's the sum. So two methods in order to make the model away from the training data. Okay, so this reduces the overfitting. So what is overfitting? The model perfectly fit the training data but doesn't too much fit unseen data. So we try actually to make a little bit of decorrelation between the model and the training data. And this is just a summary table between the lasso and the bridge regularization techniques. This is called L1 norm, and this is called the L2 normalization. Okay, that's pretty much it for linear regression. I think now we took linear regression from different perspectives, from objective function, loss minimization, and also from OLS perspective, machine learning perspective. Starting from the next lecture, we're going to start about classification problems. Now, we've done a lot with regression. We're going to talk about classification. We've already done one model for classification. What is the classification model that we've done so far? Logistic regression. Yes, and now we're going to generalize for other types of classification models. Any question?
So lasso and bridge or bridge?
Bridge. It's to avoid overfitting.
So a different form of linear regression.
Yes. Just which, because linear regression is going to optimize the mean square error, and this is going to be a modified version of mean square error. Okay. When you change the loss function, the final coefficients, the model is going to change slightly. Okay.